Picture this. You're an archaeologist, not the kind that brushes dirt off pottery shards in some sun-baked field. You're the kind who works at the edge of what science can explain. You've spent your career digging through layers of rock, reading the planet like a book. And one afternoon, somewhere deep in a canyon in the American Southwest, your team pulls something out of the earth that shouldn't exist. It's machined metal, not shaped by erosion, not a natural formation. Machined, precise angles, uniform density, buried under 50 million years of sedimentary rock. You sit with it in your hands, and you feel the world tilt slightly beneath you. Because if this is real, if this is what it looks like, then everything we think we know about the history of intelligent life on this planet is wrong. Now, that specific scenario is fictional. I want to be clear about that. But the question it raises? That question is one of the most serious, most mind-bending, and most genuinely unsettling ideas that actual, credentialed scientists have ever put into print. And it goes like this. What if we are not the last civilization on Earth? What if hundreds of millions of years before humans ever walked these continents, some other form of intelligent life rose up, built something, left its mark on the world, and then vanished so completely that we have never, not once, found a single, undeniable trace of it? What if the reason we feel so alone in our own history is not because we are the first, but because whatever came before us was simply too old for us to find? This is not a fringe theory. This is not ancient aliens. This is a hypothesis that was seriously proposed in 2018 by two researchers at NASA and a university geology department. It has been discussed in peer-reviewed scientific literature. It touches on fields as wide-ranging as paleontology, geology, climate science, thermodynamics, and the search for extraterrestrial life. It also forces a question that most of us have never had to seriously ask. What do we actually know about the deep history of intelligence on this planet? Not what do we assume, not what feels intuitively obvious. What do we actually, rigorously, scientifically know? And when you sit down and try to answer that question honestly, when you really interrogate the methods and the evidence and the limits of our instruments, the answer turns out to be far less comfortable than most people expect. And once you hear it, really hear it, you will never look at the ground beneath your feet quite the same way again. Stay with me, because where we're about to go is going to challenge something very deep in the way you think about time, about intelligence, and about what it means to leave a mark on the universe. Chapter 1: The Abyss Beneath Our Feet. Let's start with something deceptively simple. How old is the Earth? About 4.5 billion years. You've probably heard that before. It's one of those numbers that gets thrown around so casually that it stops meaning anything. 4.5 billion years. Okay, sure, big number. But let's try to actually feel that number for a second. Imagine you compressed all of Earth's history into a single calendar year. January 1st is the formation of the planet. Right now, this moment, you watching this video, is the final stroke of midnight on December 31st. On that calendar, the dinosaurs don't go extinct until December 26th. The entire Roman Empire, the pyramids, every war ever fought, every book ever written, every city ever built, all of human civilization happens in the final 11 seconds of December 31st. 11 seconds out of 365 days. Now here's what I want you to hold in your mind. Complex animal life on Earth didn't begin until roughly 540 million years ago. That's the Cambrian explosion, the moment the fossil record suddenly explodes with strange, elaborate creatures. On our calendar, that's around November 17th. That means there are nearly 11 full months of Earth's history that happened before anything we'd recognize as complex life even existed. But then, and this is where it gets interesting, complex life has had over 540 million years to do its thing on this planet. That is an almost incomprehensible stretch of time. And here's the thing about that time. It is not empty. The fossil record shows us wave after wave of life flourishing, evolving, dying, recovering, evolving again. Mass extinctions that wiped out the majority of species on the planet, followed by explosive radiations of new forms. And somewhere in that 540 million year span, scattered across dozens of geological periods, there are creatures that display what scientists call encephalization. That is, a trend toward larger brains relative to body size. There are animals that used simple tools. There are animals with remarkably sophisticated social structures, communication systems, problem-solving abilities. We tend to think of intelligence, genuine, technology-producing intelligence, as something that only happened once. Here, with us. But why? Why would we assume that in 540 million years of complex life on this planet, the spark of intelligence only caught fire once? Think about what that assumption actually requires you to believe. It requires you to believe that in nearly 500 million years of evolving, adapting, competing, and surviving, life on this planet only stumbled onto the specific combination of traits: large brain, manipulative hands, social communication, planning ability. Exactly once. And that once was us. In the last geological eye blink. In the final 11 seconds of the year. That's not a scientific conclusion. That's an assumption dressed up as one. Now, to be fair, there are reasons people believe it. The main reason is the argument from silence. We've been digging up the earth for hundreds of years, and we haven't found any ancient cities or tools or machines that predate human civilization. If something intelligent was here before us, wouldn't we know? And that's a reasonable intuition. It's just wrong for reasons that are much more interesting than the intuition itself. The answer most people give is because we'd find evidence of it. We'd find ruins, artifacts, some signature of a technological civilization in the geological record. And here is where the story gets truly strange. Because when you actually sit down with geologists and paleontologists and ask them, honestly, rigorously ask them, what would we expect to find if a technological civilization existed 50 million years ago? Or 100 million years ago? Or 300 million years ago? The answer is deeply, profoundly unsettling. We might find almost nothing at all. Chapter 2: The problem with deep time. Here's something most people don't appreciate about the fossil record. It is extraordinarily incomplete. Not a little incomplete. Not mostly complete with some gaps. Extraordinarily, almost absurdly, incomplete. The conditions required for an organism to become a fossil are incredibly specific. It has to die in the right place, near sediment, usually underwater or in a floodplain. It has to be buried quickly enough that scavengers don't destroy it and decay doesn't consume it. The sediment has to mineralize around it properly. And then that fossil has to survive millions of years of tectonic activity, erosion, heat, pressure, and chemical change. And then finally, it has to end up close enough to the surface that some human being, in the brief window of time before erosion destroys it again, happens to find it. The paleontologist Peter Dodson once estimated that we have likely discovered fossils of less than 1% of all species that have ever lived. Less than 1%. Which means that 99% of everything that has ever walked, crawled, swum, or flown across this planet has left absolutely no trace that we've found. But organisms are just the beginning of the problem. Let's talk about what happens to structures, buildings, roads, any manufactured object left in the environment without maintenance. Most structures humans build are made from wood, clay, fired ceramic, concrete, or metal. How long do these last? Wood, under typical surface conditions, may be a few hundred years before it degrades completely. Even in the most favorable dry conditions, think ancient Egyptian artifacts preserved by desert air, we're talking a few thousand years, at most, before it's unrecognizable. Concrete is more durable, but it still erodes and fractures over millennia. The most impressive Roman concrete structures, some of the most durable ever made, will be geologically undetectable within a few million years. Metals corrode. Most of them disappear into oxides and soil chemistry within tens of thousands of years. Even the most corrosion-resistant metals, like platinum or gold, would, over deep geological timescales, be dispersed, diluted, subducted into the mantle, or chemically altered beyond recognition. Plastics are an interesting case. We actually generate an enormous amount of plastic, and there is genuine scientific debate about whether a thin plastiglomerate layer, plastic melted into rock, might survive in the geological record for millions of years. But over hundreds of millions of years? The polymer chains break down. What remains would be a faint chemical signature at best. Now here's the key question. If a civilization existed on Earth 50 million years ago, what geological layer would contain evidence of them? 50 million years ago is the Eocene epoch, and here's the brutal truth. The Eocene surface is now buried under tens to hundreds of meters of subsequent sediment in most places, actively being subducted under tectonic plates in others, or has been completely erased by erosion or metamorphism in still others. The fraction of the Eocene surface that is both A, preserved, and B, accessible to human researchers is tiny. Now push that back further. 100 million years ago, the Cretaceous. 200 million years ago, the Triassic. 300 million years ago, the Carboniferous. With each step back in time, the percentage of that era's surface that survives in accessible form shrinks dramatically. And here is the truly vertiginous part. The older the potential civilization, the more completely its physical evidence would have been erased. A civilization from 300 million years ago would have existed before the supercontinent Pangaea fully broke apart. The entire continental configuration of the Earth was different. Mountain ranges that existed then have been ground to nothing. Ocean floors from that era have been almost entirely consumed by subduction. The very rocks that would have recorded the evidence of such a civilization are, for the most part, simply gone. Let me put some numbers on this because the scale of the destruction is hard to overstate. The oceanic crust, the seafloor, is constantly being created at mid-ocean ridges and consumed at subduction zones. The oldest oceanic crust on Earth today is only about 280 million years old, and that's a tiny sliver near the Mediterranean. The vast majority of the ocean floor is less than 200 million years old. Everything older has been swallowed back into the mantle and recycled. That means any civilization that existed primarily on oceanic islands or on coastal lowlands that are now underwater, their entire physical territory has been destroyed by plate tectonics. Completely. Not eroded, not buried, literally consumed by the Earth itself at temperatures of over 1,000 degrees Celsius. The continental crust is more stable, but it too is under assault. Mountain ranges rise, and then over millions of years, erosion grinds them down to nothing. The Appalachian Mountains, which today are modest in height, were once likely as tall as the Himalayas, and hundreds of millions of years of erosion have removed kilometers of rock from their surface. Whatever was on that rock surface is gone. This is what geologists call deep time. And the deeper you go into it, the more terrifyingly empty the record becomes. Not because nothing happened, but because the record-keeping system of the Earth itself is lossy, impermanent, and ultimately destructive of most of what it encodes. So when we say, we've found no evidence of a prior civilization, we need to be very precise about what that actually means. It means, in the fraction of ancient geological layers that are preserved, accessible, and have been examined by trained scientists, which is itself a tiny fraction of the total, we have found no unambiguous artifact of a prior technological civilization. That is a very different statement than no prior civilization existed. And it was precisely this distinction that led two scientists, in 2018, to write a paper that would quietly explode across the scientific community. Chapter 3, the Silurian Hypothesis. In April of 2018, Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester, published a paper in the International Journal of Astrobiology. The title was The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name is a nod to a 1970 episode of Doctor Who, in which a species of reptilian humanoids called Silurians inhabited the Earth hundreds of millions of years before humans and retreated underground before humans evolved. Schmidt and Frank borrowed the name not because they believed anything like this happened, but because it captures the essence of the question. Their paper is careful, measured, and rigorously scientific. They are not claiming a prior civilization existed. They are asking a very different question. If one had existed, what would the geological signature look like? And would we be able to detect it? The answer they arrive at is, to put it plainly, disturbing. They begin with what they call the probe, the clearest possible signal of our own industrial civilization as it would appear in the geological record millions of years from now. What would future geologists or alien archaeologists find if they drilled through the strata of our era? The answer, Schmidt and Frank conclude, is a chemical anomaly. Specifically, they point to several things. First, a spike in carbon isotopes consistent with the rapid burning of fossil fuels. When we burn coal, oil, and gas, we release carbon that has a distinctive isotopic signature. It's depleted in the heavier carbon-13 and carbon-14 isotopes relative to the lighter carbon-12. This creates a detectable ratio shift in the geological record, sometimes called a carbon excursion. Second, a spike in nitrogen isotopes from industrial agriculture and fertilizer use. Third, a massive increase in sediment erosion rates from large-scale land clearing and agriculture. Fourth, unusual concentrations of certain metals, lead, aluminum, rare earth elements, in patterns inconsistent with natural geological processes. Fifth, the aforementioned microplastics and plastiglomerate layers. Sixth, and perhaps most provocatively, a rapid global warming event, detectable as a thermal anomaly in the isotopic record of ocean sediments. Now, here is where the paper becomes genuinely stunning. Because when Schmidt and Frank look back through the geological record for events that match this kind of profile, anomalous carbon excursions, rapid warming events, unusual isotopic signatures, they find them, not just one, several. The most famous is the Paleocene-Eocene thermal maximum, or PETM, which occurred about 56 million years ago. In the PETM, the Earth's temperature spiked by 5 to 8 degrees Celsius over a geological eye blink, perhaps as little as 20,000 years. This was accompanied by a massive negative carbon isotope excursion, a sudden shift in the carbon-13 to carbon-12 ratio that has never been fully explained. The leading hypothesis is a natural source, volcanic activity, or the sudden release of methane from ocean floor deposits called methane hydrates, perhaps triggered by orbital changes. These are plausible explanations. But Schmidt and Frank point out something remarkable. The PETM's carbon isotope excursion is, in many ways, chemically similar to what we would expect to see if a prior industrial civilization had rapidly burned through a large reservoir of fossil fuels. There are other events too. The end Permian extinction, 252 million years ago, is the most severe mass extinction in Earth's history. It killed something like 90% of marine species and 70% of terrestrial vertebrate species. It too is associated with massive carbon isotope anomalies, rapid warming, and geochemical disruptions that, in some models, have not been fully accounted for by the volcanic activity of the Siberian traps alone. But there's another event that Schmidt and Frank examine that gets less attention, and it's one I find particularly fascinating: the Tourcian Oceanic Anoxic event, which occurred approximately 183 million years ago during the early Jurassic. This event involved a rapid carbon isotope excursion, a sudden warming, a significant marine extinction pulse, and widespread ocean anoxia, oxygen depletion in the oceans. The trigger is generally attributed to the eruption of the Karoo-Ferrar Large Igneous Province. But the carbon excursion during the Toarcian event has some features that models of the volcanic trigger struggle to fully reproduce, including its rapidity and the specific pattern of isotopic fractionation. None of this is proof. Each of these events has a perfectly reasonable natural explanation. The point Schmidt and Frank are making, and it's a point worth sitting with, is that our ability to distinguish between a natural carbon excursion and one partially caused by industrial activity is fundamentally limited by the resolution and completeness of ancient geological records. We are pattern matching in a noisy signal, and the noise at these timescales is very, very loud. Schmidt and Frank are not saying these events were caused by ancient civilizations. They are saying something more subtle and in some ways more disturbing. We cannot currently rule it out using only the geological evidence available to us, because the geological record at these timescales is simply too degraded, too incomplete, and too ambiguous to deliver a definitive verdict either way. They calculate, in fact, that if a civilization similar to ours existed on Earth 50 million years ago, burning fossil fuels, farming at scale, building infrastructure, its chemical signature in the rock record would have been substantially degraded even by now, and might appear as little more than a modest isotopic anomaly. The kind of anomaly we see, for example, in the PETM. This is the Silurian hypothesis in its most rigorous form, not a claim, but a methodological challenge. It is an invitation to ask, with genuine scientific seriousness, whether the absence of evidence for a prior technological civilization is actually evidence of absence, or whether we are simply not yet looking in the right way, with the right tools, for the right signatures. And that question, once asked, pulls at threads that run through the entire history of life on Earth. Chapter 4. Who could have come before? Let's take a step back from the geology for a moment and think about biology. If a technological civilization did arise on Earth before humans, before even the ancestors of mammals, what might it have looked like? What kind of creature, from the vast parade of life that has moved across this planet, could have developed the kind of intelligence we associate with technology-producing civilization? This is not idle speculation. It's a way of stress testing the hypothesis and figuring out when and where such a civilization would have been plausible. The first and most obvious constraint is time. You need enough time for evolution to produce complex multicellular life, and then for natural selection to produce increasingly sophisticated nervous systems, and eventually the kind of brain that can plan across years, communicate symbolically, and manipulate materials with fine motor control. The Cambrian explosion, again, is the starting gun. Before roughly 540 million years ago, there is almost nothing in the fossil record that could have served as the ancestor of a complex brain-having animal. Simple sponges, algal mats, the enigmatic ediacaran organisms. Nothing with the neurological architecture that could, even in principle, scale up to intelligence. After the Cambrian, though, the story changes. Within about 50 million years of the Cambrian, by about 490 million years ago, you have fish. Primitive, jawless fish, but fish nonetheless. Creatures with spinal cords, bilateral symmetry, rudimentary brains. The basic vertebrate body plan that would eventually produce, among many other things, us. By 300 to 75 million years ago, you have the first four-limbed vertebrates crawling out of the water. And by 330 million years ago, the Carboniferous period, you have a world that is, in some important respects, almost modern. There are forests, there are insects, some of them enormous, flying through a thick oxygen-rich atmosphere. There are reptiles, amphibians, synapsids, the lineage that would eventually produce mammals. The Carboniferous lasted from about 358 to 298 million years ago. It is famous for two things. First, its vast, swampy forests of club mosses and tree ferns, forests that when they died and were buried became the coal seams we have been burning since the Industrial Revolution. Second, an extraordinary explosion of arthropod diversity, including some of the most alien-looking creatures that have ever existed. But here's what I want you to focus on. In the Carboniferous, you have warm-blooded ancestors of mammals, the synapsids, already evolving. You have creatures with complex nervous systems. You have social behaviors appearing in some lineages. You have, in other words, the raw material. Could a synapside of the Carboniferous have evolved over tens of millions of years toward something resembling technological intelligence? In principle, possibly. The problem is what happened next. At the end of the Permian, 252 million years ago, the Great Dying hit. That 90% marine extinction, that 70% terrestrial vertebrate extinction. Whatever evolutionary progress had been made in the Permian was, for the most part, catastrophically reset. The survivors were, almost by definition, the generalists, the creatures that could eat almost anything, live almost anywhere, and reproduce fast enough to weather an apocalypse. This is actually a pattern we see repeatedly in the history of life. Mass extinctions act as hard resets. They destroy the highly specialized, the ecologically dominant, the cognitively complex, and they replace them with the small, the fast-breeding, the adaptable. After the end Cretaceous extinction that killed the non-avian dinosaurs, it was the small, nocturnal, insect-eating mammals that inherited the Earth. And it took those mammals tens of millions of years to re-evolve the kind of ecological dominance and encephalization that the dinosaurs had achieved. But here's the fascinating flip side of that. After the KPG extinction, the one that killed the dinosaurs, encephalization in mammals accelerated remarkably fast. Within roughly 10 million years, you see a dramatic increase in brain-to-body size ratios across multiple mammalian lineages. The open ecological niches left by the dinosaurs created evolutionary pressure for intelligence, and evolution responded. This suggests something important. Intelligence is not a 1 in a billion accident. It is, apparently, something that evolution converges on, repeatedly and relatively rapidly, when ecological conditions favor it. It has evolved independently, not through shared ancestry. In mammals, in birds, ravens, parrots, corvids, in cephalopods, octopuses, cuttlefish, and arguably in certain fish. The octopus case is particularly striking. Octopuses have nervous systems radically different from ours. Most of their neurons are distributed throughout their arms, not centralized in a brain. Yet they display remarkable problem-solving ability, tool use, play behavior, and even what appears to be dreaming. They evolved their intelligence entirely independently of the vertebrate line, from a common ancestor that lived perhaps 600 million years ago. What makes the cephalopod case so important to this discussion is not just the intelligence itself, it's the speed at which it evolved. Cephalopod brains, relative to their body size, are among the largest of any invertebrate. And this happened despite cephalopods having a lifespan of only 1 to 2 years in most species. Short-lived animals typically don't evolve large brains because the metabolic cost of a large brain takes time to pay off. The fact that octopus intelligence is as sophisticated as it is, given these constraints, suggests that the evolutionary pressures driving intelligence were extremely strong. It's convergent evolution doing something remarkable, taking an entirely separate body plan and arriving, through a completely different route, at the same functional destination, a creature that can think, plan, and solve problems. And here's the broader point. Cephalopods have existed for over 500 million years. During the Cretaceous, ammonites, cephalopods related to today's nautiluses, were among the most diverse and ecologically successful marine animals on the planet. We have no evidence they were intelligent. But their existence and the intelligence we see in their surviving relatives is a reminder that evolution does not have a single destination, and that intelligence is not our exclusive inheritance from a lucky past. If intelligence evolves independently in so many different lineages under modern conditions, is it so hard to imagine that it might have done so before? In the long sprawl of the Carboniferous? In the warm, productive Cretaceous? In the Eocene, before the cooling that would eventually lead to our Ice Age cycles? There is one lineage that paleontologists occasionally point to when this question comes up: the Maniraptorans. Maniraptorans were a group of dinosaurs, the same group that gave rise to modern birds, that displayed some of the highest encephalization quotients of any non-avian dinosaur. The therizinosaurs, the troodontids, the dromaeosaurids like Velociraptor. These were animals with relatively large brains, forward-facing eyes providing binocular vision, grasping, hands with opposable or semi-opposable digits, complex social behaviors, and in some cases, evidence of parental care. The Canadian paleontologist Dale Russell in 1982 famously performed a thought experiment. He took the troodontid dinosaur Troodon, one of the most encephalized dinosaurs known, with a brain-to-body ratio approaching that of some modern birds, and applying the same scaling laws that describe human evolution, extrapolated what a Troodon lineage might have looked like if the end Cretaceous extinction had not occurred and encephalization had continued for another 50 million years. The result, which Russell called the dinosauroid and physically modeled in 3 dimensions, was controversial, probably too anthropomorphic, and almost certainly wrong in its specific details. But the underlying question it raised was legitimate. Given enough time, could Maniraptorans have evolved technological intelligence? The honest answer is, we don't know. But the reasons for skepticism are not as airtight as they might seem. The lineage had the neural architecture, the manipulative forelimbs, the social complexity, and crucially, 100 million years during the Cretaceous in which to develop further. The asteroid that ended all that was not inevitable. It was, from a statistical standpoint, a rare event, the kind of catastrophic contingency that Stephen Jay Gould famously argued makes the emergence of any particular intelligent species vanishingly improbable. But Gould's argument cuts in an interesting direction here. If contingency is everything, if the emergence of intelligence is not driven toward any particular body plan or lineage, but is simply what happens when ecological pressure and sufficient time combine, then the history of a 4.5 billion-year-old planet with 540 million years of complex animal life seems like it ought to have produced more than one shot at it. Unless those shots happened and we simply haven't found the evidence. Chapter 5. The evidence we'd actually expect. Let's get very concrete. If an industrial civilization existed on Earth, let's say 50 million years ago, because that's both recent enough to be plausible and old enough to be geologically challenging, what would we actually be looking for? Schmidt and Frank's paper provides a framework, but it's worth going through the specific categories in detail, because this is where the hypothesis moves from philosophy into actual science. Isotopic anomalies in the carbon record. This is the strongest potential signal. Industrial civilization burns fossil carbon. It also produces agricultural nitrogen. Both of these would leave detectable isotopic signatures in marine sediments, specifically in the carbonate shells of foraminifera, the microscopic oceanic organisms that are preserved in astonishing quantities in deep sea sediment cores. The good news, we have those cores. We have drilled through millions of years of ocean sediment and analyzed the isotopic ratios in remarkable detail. The bad news, the signal of a 50-million-year-old industrial civilization, assuming it lasted a few thousand years, like ours has so far, would appear in those records as a relatively brief and modest carbon excursion, easily confused with natural variability or other geological processes. And as mentioned, events like the PETM do produce exactly that kind of anomaly. We have attributed the PETM to natural causes, and those explanations are plausible. But could we definitively rule out an industrial component? Schmidt and Frank say honestly, no, not with current methods. Heavy metal enrichment. Industrial activity concentrates certain metals, lead, zinc, copper, rare earth elements, in ways that natural processes don't. We see this very clearly in Arctic and Antarctic ice cores, where the spike in atmospheric lead from Roman-era smelting is clearly visible as a thin chemical layer. For modern industrial civilization, the spike is dramatically larger. At 50 million years remove, would this signature survive? Possibly in marine sediments. The geochemical cycling of heavy metals in ocean sediments is relatively slow, and unusual concentrations might persist as detectable anomalies. But the signal would be severely degraded, and it would require extraordinarily careful analysis to distinguish from natural geochemical variation. Erosion signatures. Large-scale agriculture dramatically increases erosion rates. The clearance of forests, the plowing of fields, the diversion of rivers. All of these mobilize sediment in ways that leave a detectable signal. Sudden increases in the sedimentation rate in downstream lakes and ocean margins, changes in the grain size and composition of sediment. A shift in pollen records from forest species to grassland and crop species. This is actually one of the cleaner signals of human civilization in the geological record. Archaeological sediment cores from river deltas around the world show clear spikes in sedimentation rate coinciding with human agricultural expansion. At 50 million years remove, much of this would be erased, but in unusually well-preserved sedimentary sequences, anomalous erosion events are not impossible to detect. The thermal anomaly. This is subtle but potentially powerful. If a prior civilization drove a warming event, even a modest one, that warming would have altered sea surface temperatures, modified carbonate chemistry in the oceans, and shifted the ecological balance in ways that might be detectable as brief but unusual perturbations in the fossil record. Not individual fossils of cities or machines, but ecological disruptions. Sudden local extinctions of temperature-sensitive species. Range shifts. A brief window of anomalous biodiversity stress. Again, we would need to distinguish this from natural variability. But the tools of paleoclimatology are increasingly sophisticated, and the resolution of ancient climate records is improving every decade. The hardest problem: physical artifacts. Here is where even the most generous framing of the Silurian hypothesis runs into serious trouble. Physical artifacts, objects made from processed materials, are extraordinarily unlikely to survive 50 million years in recognizable form. Not impossible, but extraordinarily unlikely. Even ceramics, which are among the most durable materials humans produce, weather and dissolve over geological timescales. Even if an artifact somehow survived, it would need to be in a geological context where it could be recognized as artificial rather than a natural mineral formation. And at 50 million years, that context would be deeply ambiguous. There is one candidate material worth mentioning: manufactured glassy materials. Certain industrial processes produce glasses, silicate materials fused by high heat, that have unusual compositions inconsistent with natural volcanic glasses. Tektites, the glassy, objects produced by asteroid impacts, survive for millions of years. A manufactured glass of unusual chemical composition, if it were ever found in ancient strata, would be difficult to explain as anything other than the product of a high-temperature industrial process. It would be, in essence, an impossible object, something that the chemistry of the natural world cannot produce without the application of deliberate, directed intelligence. And if we ever found one in a 100-million-year-old rock formation, it would be the most important discovery in the history of science. But we have not found such objects in Eocene or older strata. And here is the honest, clear-eyed bottom line that Schmidt and Frank arrive at in their paper. If a prior industrial civilization existed on Earth, but existed long enough ago, and especially if it lasted only a few thousand years, as ours has so far, the probability of us having already found definitive evidence of it is low. Not zero, but genuinely, uncomfortably low. We are, they suggest, in the position of someone trying to find a needle in a haystack the size of a continent, using tools we only recently invented, having so far searched perhaps a few city blocks of that continent. The haystack is real, the tools are improving, but honesty demands that we acknowledge that the search has barely begun. The absence of evidence in this case is not very strong evidence of absence. Chapter 6: The Fermi Paradox Turned Inward. Now I want to take everything we've established and turn it in a direction that I suspect you haven't considered. You've probably heard of the Fermi Paradox. It's the famous puzzle posed by physicist Enrico Fermi in 1950 during a lunch conversation at Los Alamos. The observable universe is roughly 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies, each containing hundreds of billions of stars, many of which have planets. The conditions for life, as far as we can tell, are not rare. Given enough time and enough planets, intelligent life should have arisen many times. Some of those civilizations should be ancient enough to have spread across the galaxy many times over. So where is everybody? That's the Fermi Paradox. The universe appears old enough and large enough to be teeming with intelligent life, and yet we see no evidence of it. There are dozens of proposed solutions to this paradox. Maybe intelligent life is genuinely rare. Maybe civilizations inevitably destroy themselves before they can spread. Maybe advanced civilizations become undetectable by choice. maybe the galaxy is full of signals we haven't learned to recognize yet. But here is the Silurian hypothesis' twist on this classic puzzle, and it is genuinely one of the most unsettling ideas I have encountered in science communication. What if the answer to the Fermi paradox is not out there, but here? What if the reason we feel so alone in the universe is not because intelligence is rare across the cosmos, but because the most obvious example of intelligence arising on a habitable planet, developing technology, and leaving traces that are nearly impossible to find, happened right here on Earth before we existed? Think about what this means for the Drake equation, the famous formula for estimating the number of communicating civilizations in the galaxy. One of its key variables is L, the average lifespan of a technological civilization. We typically imagine this in terms of millennia or millions of years, either because civilizations thrive and expand for a long time, or because they destroy themselves quickly. The seedy community has spent decades arguing about the value of L, but the Silurian hypothesis introduces a variable that the Drake equation never contemplated: temporal layering. On a single planet, over geological time, multiple civilizations might arise and fall, each one separated from the next by millions or tens of millions of years of evolutionary reset, each one nearly invisible to its successor. If this is true for Earth, and we cannot rule it out, then it might be true for other planets as well. Planets that we, in our SETI searches, categorize as uninhabited might simply be planets that have passed through the aftermath of a civilization that rose and fell before anyone was looking. Or they might be planets currently in the geological silence between one civilization's end and another's beginning. The universe, in this framing, is not silent because intelligence is rare. It might be silent because the timescales of intelligence are brief compared to the timescales of planets. A planet that hosts 3 separate civilizations over 500 million years is at any given moment almost certainly silent and apparently empty. Only during the tiny windows when a civilization is actually present and transmitting would it be detectable. And we would not know from the outside how many civilizations had come before. This has a name in the astrobiology literature. It's sometimes called paleocontact, or more precisely, the hypothesis of serial intelligence. And while it remains speculative, it is a hypothesis with genuine scientific content. It makes predictions that could, in principle, be tested. It suggests that we should look more carefully at isotopic anomalies in the geological record, not just as curiosities, but as potential biosignatures of technology. It suggests that planetary science, when applied to exoplanets, should include not just a search for current life, but for the geochemical afterglow of past life, what some researchers call technosignatures embedded in ancient strata. And it suggests something else, something about the nature of civilizations themselves. We tend to think of our civilization as the logical endpoint of a long journey. Evolution spent billions of years producing cells, then complex organisms, then brains, then language, then fire, then agriculture, then industry, then the internet, and here we are, the pinnacle, the culmination, the species for whom the whole history of life on Earth was, in some sense, the prologue. The Silurian hypothesis demolishes that narrative completely. If intelligence is something that arises repeatedly over geological time, if it is less a singular destination than a recurring event, then we are not the point of the story. We are not even particularly special in the story, except in the most contingent, arbitrary way. We are the ones who happen to be alive right now, in this brief geological window, looking backward at a past that may be far more populated with minds than we ever imagined. And, more unsettlingly, we are the ones who are generating the geological record that a future species, perhaps tens of millions of years from now, will try to read. We are currently laying down the strata. We are right now depositing the carbon excursion, the metal enrichment, the plastic-glomerate layer, the erosion signal. We are, at this very moment, becoming the potential Silurians for whoever comes next. Whether they will find us, whether our chapter in the rock record will be legible to the intelligence that follows us, depends on how long we persist and what we leave behind, and how good their instruments are. And that question, whether the next intelligence on Earth will know we were here at all, is perhaps the most quietly devastating thing about this entire idea, and it suggests something deeply personal about our own position in time. If we are not the first, if some form of intelligence preceded us on this planet, perhaps multiple times, then our civilization is not the protagonist of Earth's story. We are one chapter, maybe not even the last one. That is either the most humbling thought you've ever encountered, or the most terrifying, or if you sit with it long enough, somehow, both. Chapter 7. How fast does a civilization disappear? Here's an experiment I want you to run in your imagination. It is the year 2025. Every human being on Earth vanishes overnight. Not destroyed, just gone. The cities are intact. The power plants are idle. The roads are empty. The supermarkets are full of food beginning to rot. Every artifact of our civilization, every building, every car, every plastic bottle, every nuclear power plant, every bridge, every book, is left exactly where it is. Now ask yourself, how long before there's nothing left? This is not a hypothetical exercise in nihilism. It's one of the most important questions you can ask if you want to understand the Silurian hypothesis, because the answer tells you how demanding the geological record really is, and how quickly even an advanced technological civilization can be erased by nothing more than ordinary physics and chemistry. The journalist Alan Weisman explored this in remarkable depth in his 2007 book, The World Without Us, and his findings are genuinely startling. Within days of human disappearance, the subway systems of major cities begin to flood. Most subway infrastructure is kept dry only by continuous pumping. Without power, the pumps stop, and within 48 hours, tunnels fill with groundwater. Within months, unheated buildings in temperate climates begin to deteriorate rapidly. Water infiltrates through cracked seals. Freeze-thaw cycles crack concrete. Vegetation begins to colonize rooftops and pavement, their roots working into every fissure. Within decades, most wood-framed structures collapse. The great skyscrapers of New York and Chicago, built from steel and glass, begin to lose their glass as sealants fail and wind works at the frames. Steel, exposed to moisture and oxygen, rusts. And without maintenance, the structural steel of even the most robust buildings begins to lose integrity within a century or two. Within 500 years, almost every building on Earth would be unrecognizable. Most would be rubble. The forests would have reclaimed most temperate cities. In a few thousand years, the rubble itself would begin to be buried under layers of sediment deposited by flooding rivers and shifting soil. Now, some things last longer. The Great Pyramid of Giza would still be standing after 10,000 years, though heavily eroded. The foundations of our largest structures might leave subtle depressions in the landscape that remain detectable for hundreds of thousands of years. Some plastics would persist for perhaps 1 million years in certain environments before breaking down completely. But here is the critical number. Geologists estimate that after approximately 10 million years, essentially no surface structure built by human technology would remain identifiable as artificial. The materials would still be there, dispersed, chemically altered, mixed into sediment, but the structures themselves would be gone. 10 million years. That sounds like a long time, but in the context of the Silurian hypothesis, 10 million years is nothing. The question is about civilizations that might have existed 50, 100, or 300 million years ago. At those timescales, even the 10 million year survivors are gone. The dispersed materials are diluted beyond detection in most cases. The sediment layers that once contained our cities are either deeply buried, tectonically deformed, metamorphosed by heat and pressure, or simply eroded away. There is something almost vertiginous about this when you let it sink in fully. Our civilization, with its 8 billion people, its satellites, its nuclear weapons, its global internet, its towering cities, its vast agricultural systems covering nearly half the land surface of the planet, would, after 50 million years, leave a geological signal roughly the size of a comma. A brief chemical whisper in a few well-preserved sediment cores. A faint isotopic anomaly. Maybe, a thin layer of unusual trace metals in deep sea sediments. That's it. That's all that would be left of everything we've built. Now, reverse the lens. Turn it backward in time. If another civilization, not human, perhaps not even mammalian, existed on Earth 56 million years ago, and it burned through its fossil fuels and altered its climate, and then vanished in a geological instant, what would we expect to find? Exactly what we actually find in the geological record of the Paleocene-Eocene thermal maximum. A brief carbon isotope anomaly, rapid warming, a pulse of ocean acidification, an unusual biodiversity disturbance, and then nothing. Silence. The rock closes over it like water over a stone, and the only trace is a faint chemical echo in ancient marine sediments that we are only now, with our most sophisticated instruments, beginning to read. I'm not telling you the PETM was caused by an ancient civilization. The volcanic and methane release hypotheses are well supported and probably correct. What I am telling you is this. If we wanted to design a geological signature for a prior industrial civilization that had been running for a few thousand years, we could not design one that looked more like the PETM than the PETM itself. That's not proof. It's not even strong evidence. But it is a question that deserves to be taken seriously. And increasingly, it is. The deeper we look into deep time, the more we realize that what we call the geological record is not a complete archive. It is fragments. It is echoes. It is the barest residue of 4.5 billion years of planetary history, filtered through tectonic violence, chemical dissolution, and the relentless grinding of erosion. And if something was here before us, something that thought and built and changed the world, even briefly, there is a very real chance that the only thing standing between us and knowing it is the thickness of time itself. Chapter 8. The Anthropocene as a warning label. Let's do something uncomfortable. Let's stop looking backward for a moment and look at the present. At us. At what we are actually doing to this planet right now. And what it means if the Silurian hypothesis is even partially correct. We are currently living through what geologists are beginning to formally designate as a new geological epoch, the Anthropocene. The word means the human era, and it marks the moment in geological time when one species began reshaping the planet on a scale comparable to the great forces of nature: volcanism, ice ages, asteroid impacts, us. The formal proposal to designate the Anthropocene as an official geological epoch has been debated for decades, and it remains technically contested among stratigraphers. But the geological case for it is hard to dispute. The Earth of the 21st century is chemically, biologically, and physically different from the Earth of the 18th century in ways that exceed anything that can be explained by natural variability alone. We have quite literally become a geological force. And when you look at the specific markers that geologists are using to define the Anthropocene, the things that will still be detectable in the rock record in 50 million years, the parallel to the Silurian hypothesis becomes almost uncomfortable in its precision. The geological markers of the Anthropocene are striking. There is a global spike in carbon dioxide in the atmosphere, the highest in at least 3 million years. There is a massive negative carbon isotope excursion from the burning of fossil fuels. There is a measurable global temperature increase. There is an unusual concentration of heavy metals, lead, cadmium, mercury, in sediments worldwide. There is a thin but globally distributed layer of fallout radionuclides from nuclear weapons testing in the 1950s and 60s, a crystal-clear chemical timestamp that will be detectable in marine sediments for millions of years. There is an explosion in erosion rates from agriculture. There is a sharp decline in biodiversity, what biologists are calling the 6th mass extinction, the first one driven by a single species. And there is, of course, plastic. Microplastics are now found in the deepest ocean trenches, in Arctic snow, in the tissues of organisms living miles below the surface. Plastiglomerate, plastic fused into rock, has been found on beaches worldwide, and some researchers believe it may represent one of the most durable physical markers of our era. Now hold all of that in mind and go back to the Silurian hypothesis. Schmidt and Frank's paper asks, if a prior civilization existed, what signature would it have left? And then it maps out the expected chemical fingerprints of industrial activity. Here is the thing that nobody talks about when they discuss this paper. That list of signatures is also a list of things we should be concerned about for a completely different reason. The carbon excursion, the rapid warming, the biodiversity disruption, the geochemical anomalies. We are generating all of them right now, at a rate that, in geological terms, is almost instantaneous. If the Silurian hypothesis is real, if a prior civilization did exist and did burn through its fossil carbon and did warm its planet, then there is a very uncomfortable implication about how that story probably ended. You don't leave a geological signature of sudden, rapid industrial activity if you managed your resources carefully over millions of years and transitioned gracefully to a sustainable energy system. That kind of civilization would leave a very different mark, or perhaps no mark at all. The kind of civilization that leaves the signature Schmidt and Frank describe is the kind that burned fast, changed its atmosphere rapidly, and then stopped. The geological record, in other words, may be quietly telling us something not just about who came before us, but about what happened to them. Think about what that actually implies. If the Silurian hypothesis is real, and if the PETM or a similar event really does represent the geochemical fingerprint of a prior industrial civilization, then we are not just looking at an interesting anomaly in the rock record. We are looking at a tombstone. We are looking at the last line of a story that ended before we began. And that story ended with rapid warming, ocean acidification, ecological disruption, and a geochemical signature that persisted in the rock for 56 million years before a species evolved that was sophisticated enough to read it. The uncomfortable parallel to our own situation is not subtle. We are currently on track to release more carbon dioxide into the atmosphere in a few centuries than was released during the PETM over its entire 20,000-year duration. We are already in the early chapters of what biologists call the sixth mass extinction, a biodiversity collapse driven by a single species making rapid, large-scale changes to the planet's chemistry, land surface, and climate. The disruptions we are generating are not merely environmental problems. They are geological events. They are the kind of changes that will be written in stone and readable by whatever intelligence comes after us. That is not an argument to despair. It is an argument to pay attention. Because if intelligence arises repeatedly on Earth over geological time, and if each iteration of intelligence tends to leave behind a chemical burn mark in the rock record, then we are currently writing the evidence that future geologists, or future intelligences, will use to answer the question we are asking right now. We are the Silurians for whoever comes next. And the question is whether we will be the Silurians who left only a brief, catastrophic spike, or whether we will be the ones who figured it out in time to leave something more. Chapter 9: The Silence of the Stones. What we've actually looked for. At this point in the argument, a reasonable skeptic raises their hand, says, "Look, all of this is philosophically interesting, but surely we've looked. Surely the entire history of geology, hundreds of years of people digging up the earth, examining rock formations, drilling ocean cores, studying ancient strata, would have turned up something by now if something was there." It's a fair challenge, and it deserves a genuinely honest answer, not a dismissive one. Skepticism is the engine of good science, and the Silurian hypothesis does not get to claim scientific credibility by immunizing itself against skeptical pressure. So let's take the challenge seriously and ask, what has the geological community actually done, and what has it actually found? Here is something worth noting first. The entire discipline of scientific geology is only about 200 years old. The tools of geochemical analysis that allow us to read isotopic ratios in ancient sediments, the mass spectrometers, the laser ablation systems, the deep-sea drilling programs, have existed for between 50 and 70 years. the deep-sea drilling program that gave us the first continuous sedimentary records from the ocean floor, began in 1968. That's within living memory. The resolution and geographic coverage of our geological sampling have improved dramatically in the last few decades, and they are still improving. In other words, we are not at the end of geological inquiry. We are at a relatively early stage of it. And what that means is that the scope of what we have examined is far smaller than it might appear from the outside. What have we actually looked for? What is the actual scope of the geological search that we're claiming has found nothing? The answer, when you examine it carefully, is both more and less reassuring than you might expect. Here is what we have genuinely accomplished. We have drilled hundreds of deep-sea sediment cores from all the major ocean basins, sampling sediments that stretch back, in some cases, more than 100 million years. We have analyzed the isotopic composition of these sediments in remarkable detail, building continuous climate records that reveal ancient warming events, glaciations, extinction pulses, and oceanic chemistry changes with a resolution of tens of thousands of years in some intervals. From these cores, we have identified dozens of significant carbon isotope excursions across geological time. We have also made significant progress on the continental geological record. We have mapped major sedimentary basins on every continent. We have drilled through ancient coal beds, limestone formations, and shale sequences reaching back hundreds of millions of years. We have examined ancient soils, called paleosols, that preserve chemical signals of past atmospheric conditions. We have analyzed the geochemistry of ancient river systems through the detrital minerals they left behind. And in all of this, we have found no object that could unambiguously be identified as the manufactured product of a prior technological civilization. No machined metal, no engineered ceramic of unusual composition, no glassy material with a chemical signature inconsistent with both volcanic and impact origins, no isotopic pattern that cannot be explained by known natural processes. But here is the critical qualifier in that statement: cannot be explained by known natural processes. The scientific method, as applied to geology, operates on the principle of parsimony. Occam's razor. When you find a carbon isotope excursion in ancient sediments, you look first for the simplest natural explanation: volcanism, methane release, orbital forcing. If those explanations fit the data, you go with them. You don't invoke an ancient civilization as your first resort. That would be terrible science. But there is a difference between the natural explanation fits and the natural explanation is definitively correct, and no other explanation is consistent with the data. For most of the anomalous events in the Sol geological record, the PETM, the torsion event, several other rapid carbon excursions, we are in the first category, not the second. The natural explanations are plausible. They are not proven beyond doubt. The models that reproduce these events still have residuals, discrepancies between what the models predict and what the data actually shows, that remain subjects of active scientific debate. Schmidt and Frank's point is not that the data demands an alternative explanation. Their point is that the data is consistent with an alternative explanation that we have historically not even considered, because the possibility of prior technological civilization was not on the menu of geological hypotheses. That is a methodological problem. Not a problem with the evidence, a problem with the questions we have been asking. It's the equivalent of a detective who, when examining a crime scene, only ever considers accidental death as the cause of death and never considers homicide. Not because the evidence rules out homicide, but because the detective doesn't believe murder is possible. The evidence might be perfectly consistent with both interpretations. But if you only look for one of them, you will only ever find one of them. This methodological blind spot has a history in science. For centuries, physicians examining patients with symptoms of vitamin deficiency couldn't identify the cause, not because the evidence wasn't there, but because the concept of vitamins didn't exist yet. The answer was invisible because the question hadn't been formed. Thomas Kuhn called this a paradigm, the invisible framework of assumptions within which science operates, which shapes not just the answers scientists find, but the questions they think to ask. The geological sciences have operated quite reasonably within a paradigm that treats intelligence as a recent and singular development on Earth. Within that paradigm, there is no reason to look for prior civilizations, and therefore no systematic looking has occurred. Schmidt and Frank's paper is, in Kuhnian terms, an anomaly-raising exercise. It doesn't overturn the paradigm. It points to a question the paradigm has been systematically avoiding and asks whether the data is actually incompatible with a different interpretation. That is how paradigm shifts begin, not with dramatic revelations, but with someone noticing that the questions we haven't been asking might have answers we haven't considered. There is also a geographic problem with our geological sampling. The continents we have best studied, North America, Europe, Australia, represent a particular and somewhat biased sample of ancient geological environments. Large swaths of Africa, South America, Antarctica, and the deep continental interiors of Asia remain far less studied. There are sedimentary sequences in these regions, particularly in Africa, where Precambrian and Paleozoic rocks are exposed at the surface, over vast areas, that have never been examined with the chemical resolution required to detect the kind of subtle isotopic anomalies that Schmidt and Frank describe. And the deep sea is, despite our best efforts, still profoundly undersampled. The ocean covers 71% of the Earth's surface. The total length of all deep-sea sediment cores ever drilled in human history represents a needle-thin sampling of an almost incomprehensibly vast archive. We have not come close to reading the whole record. We have barely opened the book. None of this is to say the evidence is there, waiting to be found. It very well may not be. The Silurian hypothesis may be a fascinating thought experiment that ultimately describes something that never happened. But the honest scientific answer to "have we looked" is, we have looked in some places, with some tools, for some signatures. We have not conducted anything like an exhaustive search, and we have only recently begun to ask the right questions. Chapter Raise 10. The Mirror World. What a non-human civilization might actually look like. Here's something worth sitting with. Even if a prior civilization existed on Earth, it probably didn't look anything like ours. This is actually one of the most important points in the entire argument, because our imagination tends to default to a kind of temporal parochialism. When we think of an ancient advanced civilization, we picture something like us, but older, Stone buildings that became metal buildings that became concrete cities. Tools that became machines that became computers. A civilization shaped like ours, but transplanted into the Cretaceous or the Eocene. But that's almost certainly wrong for several fascinating reasons. First, consider the biochemistry. The organisms that would have served as the ancestors of a non-human civilization would have evolved in a world with a different atmospheric composition, different ocean chemistry, different temperature regimes, different seasonal patterns. The Carboniferous, for instance, had oxygen levels significantly higher than today, perhaps 35% of the atmosphere, compared to our 21%. This affected the physiology of every living thing in it. Insects could grow to extraordinary sizes because they absorb oxygen through their exoskeletons. And more oxygen meant more growth was possible. Fire was more common and more intense in high oxygen environments. Any civilization arising in the Carboniferous would have had to navigate a world where fire was an even more dangerous and unpredictable force than it is for us. Second, consider the cognitive architecture. Intelligence, as we discussed, has evolved multiple times on Earth, and each time it evolved, it arrived at a different solution. Human intelligence is built around sequential language, abstract symbolic thought, and a particular kind of social cognition deeply shaped by our primate evolutionary history. Corvid intelligence is built around spatial memory, causal, reasoning, and a kind of social manipulation. Octopus intelligence is built around distributed processing, camouflage, and short-term tactical problem-solving, with no social learning to speak of. A civilization built on a fundamentally different cognitive architecture would be fundamentally different in its priorities, its tools, its structures, and its relationship to its environment. Consider what a social structure might look like for an organism that communicated through color change rather than sound, like a cuttlefish. Imagine a technology tradition built not around the transmission of knowledge through language and writing, but through chemical signaling, like ants, or through electrical fields, like the weakly electric fish of South America. These are not exotic science fiction inventions. They are cognitive tools that evolution has actually produced on this planet. Scaled up by millions of years of selection pressure toward greater intelligence, they might lead to forms of civilization so fundamentally different from ours that we would have no framework for recognizing them. A civilization descended from something like the therapsids, the synapsid reptiles that were our own distant ancestors, might have developed along lines somewhat recognizable to us, because the basic mammalian cognitive toolkit has certain universal features. But a civilization descended from cephalopods, or from the giant arthropods of the Carboniferous, or from some lineage of highly encephalized dinosaurs. The structures such a civilization would build, the tools it would use, the resources it would exploit, all of these might be so different from anything we expect that we literally would not recognize them as the products of civilization even if we found them. This is not a trivial point. One of the things that makes physical artifacts from a prior civilization so unlikely to be identified as such is that we tend to look for things that look like things we make. Rectangular buildings, straight roads, machined metal with precise tolerances, right-angle geometry. But what if a prior civilization built with organic materials, because its technology was biological rather than mechanical? What if its machines were living organisms, engineered through selective breeding, or something analogous to genetic manipulation? What if its structures were grown rather than built, in ways that, after 50 million years of fossilization, would look like nothing more than unusual patterns of organic carbon in ancient sediments? What if a cephalopod-descended civilization built its technology underwater, in materials that dissolved in seawater, in a territory that has now been subducted and consumed by the Earth's mantle? And here is perhaps the most provocative version of this question. What if a prior civilization, having mastered its own biology in the way we are beginning to master ours, transcended the need for physical infrastructure entirely? What if the endpoint of its technological development was not bigger cities and more complex machines, but a radical miniaturization, or even a wholesale migration into biological or chemical information systems that left no macroscopic physical trace? We tend to assume that advanced civilization means bigger, more visible, more impactful. But our own technological trajectory over the last century has in many ways gone in the opposite direction. The most powerful computing devices we build are smaller than a thumbnail. The most complex information systems ever created live in microscopic transistors etched in silicon. If a prior civilization traveled further down that road than we have, if it figured out how to do more with less, to embed its technology in chemistry rather than architecture, its geological trace might be genuinely invisible to any instrument we currently possess. We have, built into our search, a massive bias toward civilizations that look like us. And the universe of possible civilizations, even just the possible civilizations that could have arisen on this one planet, is almost certainly much stranger and more varied than our imaginations naturally produce. There is a term in philosophy of mind for this problem. It's called the other minds problem, the challenge of knowing that any consciousness other than your own exists, because you can only ever directly experience your own cognition. The Silurian hypothesis raises a version of this at a geological scale, the other civilizations problem. How would we even know what to look for? How do you search for something when you don't know what shape it comes in? The answer, probably, is not to look for objects at all. Objects are too fragile, too dependent on specifics of material and construction that we can't predict in advance. The answer, and this is what Schmidt and Frank are arguing, is to look for process signatures. The things that any industrial civilization, regardless of its cognitive architecture or its building materials, would inevitably do to its environment. It would use energy, large amounts of it. It would process materials, mining, smelting, concentrating elements. It would alter land surfaces, clearing vegetation, disturbing soil, changing water flow. It would produce waste, chemical byproducts that accumulate in sediments, in water, in the atmosphere. And if it relied on stored chemical energy, something analogous to fossil fuels, it would release carbon that had been sequestered from the atmosphere, generating an isotopic anomaly detectable millions of years later. These are not signatures of a specific type of civilization. They are signatures of industrial thermodynamics, and thermodynamics does not care what kind of brain is running the industry. The isotope ratios shift the same way whether the creature burning the fossil carbon has 10 fingers or 10 tentacles. That's what makes the chemical approach to searching for prior civilizations so powerful. It bypasses the question of what they looked like and goes straight to the question of what they must have done. Because any civilization capable of altering its planet on a global scale must, by the laws of physics, leave a thermodynamic trace. Chapter 11. The loneliness that isn't. There's a philosophical dimension to all of this that I haven't fully addressed yet, and I think it might be the most important one. Why does the question of whether we are alone in history matter? Not just as a scientific curiosity, but why does it matter to us as people living in the present, trying to understand our place in the world? I think the answer has something to do with a particular kind of loneliness that is unique to consciousness. It's the loneliness of being aware, of having the ability to ask the question, what came before me and what will come after? And feeling the weight of that question pressing down on you with no satisfying answer. Humans have been grappling with this loneliness in various ways for as long as we've had language. Religion addresses it by positing that our existence is witnessed and meaningful to something outside of time. Philosophy addresses it by arguing that meaning is constructed rather than discovered. Science, for the most part, has offered a picture that is both more and less satisfying than either. We are the product of blind physical processes, improbable but not unique, alone in a universe that doesn't know we're here and wouldn't care if it did. There is a particular version of this loneliness that I think doesn't get discussed enough. It's not just the loneliness of being the only intelligence in the universe. It's the loneliness of being the only intelligence in our own history, of looking back across 540 million years of life on this planet and seeing, as far as we can tell, nothing that looked back, nothing that wondered, nothing that built and thought and tried to understand. Just the slow churning of evolution, the rise and fall of species, the grinding of geological forces, and then, almost incidentally, us. That picture has a crushing quality to it. It positions human consciousness as the punchline of a very long and completely pointless joke. Billions of years of rocks and oceans and bacteria and dinosaurs and mass extinctions. And then, in the final 11 seconds, something that cares about it. The universe spent 13.8 billion years not caring, and then suddenly cares, and then will presumably stop caring in a cosmologically brief interval when we're gone. The Silurian hypothesis offers, at least potentially, a different picture. Not a comforting one in the conventional religious sense. It doesn't promise witness or meaning or continuity. But it does suggest that the emergence of something that cares might not be the end point of a long cosmic mistake, but something more like a recurring feature, a pattern. The thing that happens when matter organizes itself to sufficient complexity on a planet with liquid water and energy from a nearby star. It also reframes what we mean when we talk about the loneliness of intelligence. We typically imagine that loneliness as spatial. We are surrounded by a vast, empty universe with no other minds in it. But the Silurian hypothesis suggests that the relevant axis might not be space, but time. That the universe may be populated with minds, has been populated with minds, is being populated with minds. But that those minds are separated not by the distance between stars, but by the distance between geological epochs. The universe, in this picture, is not a vast, empty room in which we shout and hear no echo. It is a long corridor, and other voices have walked it before us, and we cannot hear them because they passed this way millions of years before we arrived. That shift from spatial loneliness to temporal loneliness changes something about how the silence feels. It makes it less like an absence and more like a delay, less like emptiness and more like the hush that falls between one note and the next. The silence is still real, but what it means, what kind of universe it implies, is different. The Fermi paradox sharpens this loneliness to an almost unbearable point. The universe is vast. The conditions for life appear to be common, and yet the cosmic silence is deafening. We shout into the void and hear nothing back. That silence, if you sit with it, can feel like the most crushing confirmation that consciousness is some kind of cosmic accident. A brief candle that flares and dies in the dark. But what if the Silurian hypothesis is right? What if the silence is not emptiness, but depth? What if intelligence, even just here on Earth, is not the anomaly we assume it to be, but something the universe does repeatedly, in wave after wave, separated by the deep intervals of geological time? There is something strangely comforting about that possibility, not because it makes us less alone in the immediate sense. We would still be separated from any prior civilization by tens of millions of years, an unbridgeable gulf of time. But because it suggests that intelligence is not an accident. It is, in some sense, what matter does when you give it long enough and the right conditions. It is, to use a word that scientists are normally uncomfortable with, something close to inevitable. And if it's inevitable, if consciousness and curiosity and the drive to understand are features of the universe rather than bugs, then the fact that we exist, that we are here asking these questions right now, is not a fluke. It is an instance of a pattern. One chapter in a story that has been written before and may be written again. That is not the same as the religious answer. It doesn't promise that someone is watching or that it matters in some transcendent sense. But it does suggest that we are not as alone as the cosmic silence implies. We are, possibly, one of many. Not many at the same time, scattered across the stars in a galaxy full of radio signals, but many across time, separated by the pages of the geological record, each civilization inheriting a world shaped by the ones before it without ever knowing it. There is a kind of solidarity in that, if you're willing to reach for it. The creatures, whatever they were, that burned through the Eocene and left their faint chemical whisper in the PETM, were in some sense doing what we are doing. They arose from the same planet. They breathed an atmosphere shaped by the same processes. They looked up at a sky containing the same sun. They asked questions, perhaps, in whatever way their biology allowed for asking, and then they were gone. And we are here now, reading the trace they left, not knowing it's a trace at all. And one day, whether in 10,000 years or 10 million, something else will be here, reading whatever trace we leave. And they will not know whether the faint isotopic anomaly in the rock beneath their feet is the fingerprint of a civilization or just the geological noise of a restless planet, unless we leave them something better than a chemical whisper, unless we build something that lasts. Chapter 12. Can we test this? The future of Silurian science. At this point, you might be wondering, is this just going to stay a thought experiment forever? A fascinating but ultimately unverifiable idea that philosophers and science YouTubers can bat around without it ever touching anything real? The answer, genuinely, is no. The Silurian hypothesis is unusual among speculative scientific ideas in that it is, in principle, testable. Not easily, not quickly, but testable. Here is how the science might actually advance. The first and most tractable avenue is higher resolution isotope geochemistry. The limiting factor in detecting a prior civilization's chemical signature in the geological record is the resolution of our measurements. When we analyze ancient sediment cores for carbon isotope ratios, we are typically averaging over thousands to tens of thousands of years, because that's how thick the sediment layers are at the timescales we're discussing. A civilization that rose and fell in a few thousand years would appear as a single data point in that averaging, barely distinguishable from noise. But analytical technology is improving rapidly. New techniques in secondary ion mass spectrometry and laser ablation ICP-MS allow researchers to analyze single microfossil shells, individual foraminifera less than a millimeter across, with extraordinary precision. By analyzing large numbers of these individually, rather than bulk sediment, it becomes possible to reconstruct past climate and chemistry at much higher temporal resolution. Within the next few decades, it may become possible to examine ancient sediment intervals at century-scale resolution rather than thousand-year resolution. Fine enough to potentially detect a brief industrial perturbation that would currently be invisible. There is an analogy here worth dwelling on. When astronomers first began studying the cosmos, the resolution of their instruments was too low to see individual stars in distant galaxies. They appeared as featureless blobs of light. As telescopes improved, those blobs resolved into individual stellar systems, each with its own complex story. The geological record is, in some sense, still in the blurry blob phase for many ancient intervals. The improvement in analytical resolution that is coming over the next generation of instruments may reveal details in the rock record that are entirely invisible to us today. The second avenue is machine learning applied to the geological record. We now have access to enormous databases of geochemical measurements from sediment cores, rock samples, and paleosol analyses accumulated over decades of research. These databases contain millions of individual measurements. No human team could ever examine them comprehensively enough to identify subtle, multivariable patterns that might indicate an anomalous event. But machine learning algorithms trained to recognize the specific combination of signatures, carbon excursion, nitrogen anomaly, heavy metal enrichment, erosion spike, thermal anomaly, occurring together in the same geological interval, could scan these databases systematically. If a prior civilization's chemical signature exists in the record, a sufficiently powerful pattern recognition system might be able to flag candidate intervals for closer examination. This is not speculative future technology. Machine learning applications in geochemistry and paleoclimatology are already being actively developed and deployed. The question of whether anyone has thought to train such systems to look for the combined signature of industrial activity, rather than just natural climate variability, is one that Schmidt and Frank's paper implicitly raises. The third avenue is expanding our geographical sampling. As mentioned, vast stretches of the world's geological record have been examined only superficially. A targeted program of deep sampling in poorly studied regions, particularly in Africa, South America, and the deep continental interiors of Asia, focused specifically on Eocene and older intervals with unusual geochemical signatures, could dramatically expand our window into the past. This is not exotic or expensive science. It is the same work that geologists have been doing for centuries, applied with new questions and new analytical tools. The fourth avenue is the one that Schmidt and Frank themselves are most excited about: planetary science. If the Silurian hypothesis describes something that can happen on Earth, it describes something that can happen on any planet with a long history of complex life. And we are, right now, developing the tools to examine the geochemical histories of other planets. The James Webb Space Telescope, launched in 2021, is capable of analyzing the atmospheric composition of exoplanets by measuring how starlight passes through those atmospheres during a planetary transit. We can, in principle, detect carbon dioxide, methane, water vapor, and other gases in the atmospheres of planets orbiting other stars. A planet with an unusual abundance of industrial gases, or the chemical aftermath of a civilization that burned through its resources and collapsed, might reveal itself to a sufficiently sensitive instrument. We have not yet found such a signal, but we have only been seriously looking for a few years at a very small sample of the hundreds of billions of planets in our galaxy. More ambitiously, future space missions to Mars, Venus, and the icy moons of the outer solar system may include instruments capable of analyzing sedimentary records for isotopic anomalies. Mars, in particular, is geologically ancient. Much of its surface dates to 3 billion years or more. And if life ever existed there, the Martian rock record may contain clues that the Earth's own rock record, far more dynamic and destructive, has long since erased. The idea of looking for technosignatures in Martian sediments may sound like science fiction, but we are already sending rovers to Mars to look for biosignatures of past microbial life. The extension of that search to include geochemical signatures of past technological civilization is, conceptually, not a large leap. And there is a conceptual expansion that Schmidt and Frank's paper implicitly calls for: the addition of paleo-technosignature analysis to the toolkit of both geology and astrobiology. Right now, when astrobiologists describe what biosignatures to look for on other planets, they think in terms of current biological processes: oxygen in the atmosphere, methane in ratios inconsistent with abiotic chemistry, complex organic molecules. They do not typically think about what the geochemical aftermath of a past technological civilization might look like. Adding that question to the research agenda would be a modest step, but a significant one. The Silurian hypothesis has, in short, opened a door that cannot easily be closed. Once you ask the question, once you take seriously the possibility that the geological record might contain signatures of intelligence we have never looked for, you cannot unask it. And science, for all its imperfections, is very good at eventually following the questions it cannot unask. Conclusion: the ground beneath your feet. We started with a story, an archaeologist, a canyon, a piece of machined metal buried under 50 million years of rock. I told you that scenario was fictional, and it is. But let me complicate that slightly before we finish. There is a class of geological curiosities known as out-of-place artifacts, objects found in geological contexts where they should not be able to exist. Some of these, when examined carefully, turn out to be misidentified natural formations or objects that found their way into unusual contexts through mundane means: erosion, human activity, simple mislabeling. Most of them, honestly, are not nearly as mysterious as the people who report them claim. The London Hammer, a 19th century iron hammer found in a Texas rock formation, is a perfect example. It sounds impossible until you understand how quickly minerals can cement around objects in the right conditions. What looks like an ancient mystery is often just chemistry moving faster than intuition expects. But the fact that we feel the need to examine them, the fact that when someone pulls a strange object from ancient rock, the first question we ask is, could this be artificial? Tells you something important about the human mind. We are pattern recognition machines. We are wired to look for the signature of intelligence in the world around us because our survival has always depended on detecting whether another mind was at work. We evolved this instinct on the African savanna, scanning the grass for the shape of a predator or the footprints of another human band. And now we turn that same instinct toward the geological record and ask, was there something here before us? That instinct, applied to the deep geological record with rigor and humility, is not superstition. It is science. It is the Silurian hypothesis in its purest form, a disciplined, methodologically serious attempt to ask whether the patterns we see in ancient rocks might, in some cases, be the signature of something that thought. So here is where we end up after all of this. The Earth is 4.5 billion years old. Complex animal life has existed for 540 million years. In that time, intelligence has evolved independently at least 3 or 4 times that we know of. Mass extinctions have repeatedly wiped the evolutionary slate clean and created new ecological opportunities that evolution has repeatedly filled with increasingly complex and cognitively sophisticated creatures. The geological record, which might preserve evidence of a prior technological civilization, is so incomplete and so degraded that we cannot say with confidence what it does and does not contain. The chemical signatures of industrial civilization, which we are generating right now in real time, would be nearly undetectable in the rock record after 50 million years. And several of the most puzzling events in the geological record, the PETM, the Torsian event, others, produce exactly the kind of anomalies that a prior industrial civilization would generate. None of that proves a prior civilization existed. Let me be absolutely clear about that. The weight of scientific evidence, such as it is, points toward natural explanations for all of these events. The absence of any unambiguous artifact of prior civilization is a real and significant data point, even accounting for the incompleteness of the record. But science is not just about what we know. It is about the questions we are willing to ask. And the Silurian hypothesis asks a question that we should have been asking all along, with genuine seriousness, with good instruments, and without assuming the answer in advance. We do not know that we are the first. We assume it. We have assumed it because it feels obvious, because our civilizations dominate the present so completely that it seems impossible anything comparable could have existed before us without our knowing. But that feeling is not evidence. That feeling is the same cognitive bias that makes it hard to imagine that the sun doesn't revolve around the Earth, the bias of assuming that what we can see is all there is. The history of science is, in large part, the history of discovering that we were wrong about our place in the universe. We are not at the center of the solar system. Our solar system is not at the center of the galaxy. Our galaxy is one of hundreds of billions. The age we live in is not special in cosmic time. The matter we are made of constitutes only 5% of the universe's mass energy content. Each of these realizations was, in its moment, a shattering revision of the human self-image. The Silurian hypothesis proposes one more revision in this tradition. Not that we are small in space, we already knew that, but that we might be small in time too. That the history of intelligence on this planet might not begin with us and proceed forward, but might be a pattern that preceded us, interrupted by catastrophe, only now reconstituting itself in a new form, with no memory of what came before. There is something almost mythological about that picture. It's the kind of thing that ancient civilizations intuited, that the world is older than we are, that there were ages before our age, that something was here before us and was lost. The flood myths, the stories of lost continents, the legends of forgotten peoples who built great things and vanished. These stories are almost certainly not literally true. But the instinct that generates them, the intuition that the world is older and stranger than our records show, might be tracking something real. The universe is old. This planet is old. Life has been doing extraordinary things on this planet for a very long time. And the ground beneath your feet, literally, physically, the ground you are standing on right now, contains a record of that history that we have only begun to read. Every layer of that record is a page in a book. Most of those pages have been destroyed. The ones that remain are written in a chemical language we are only now learning to decode. And some of those pages, we do not yet know which ones, might tell a story we were not expecting, might describe a world before our world, might contain, in the faint shift of an isotope ratio preserved in the carbonate shell of an ancient microscopic organism, the last echo of something that thought and built and burned and ended. We may never know for certain. The deep past may guard its secrets well enough that this question remains open for as long as our civilization lasts. But the act of asking it, seriously, rigorously, without flinching, changes something about how we understand ourselves. We are not the point of the story. We are a chapter. And like every chapter, we will eventually end. What happens after that? Whether the story continues, whether something else rises from the wreckage of whatever we leave behind, whether the next intelligence that looks up at this sky will know we were ever here. That is a question we cannot answer. But here is what we can do. We can ask whether we were preceded. We can look carefully at the record with humility and rigor and not assume we know what it says before we've read it. We can develop the tools to search for signatures we have never searched for before. We can add the question of prior intelligence to the agenda of planetary science, geology, and astrobiology, not as a certainty, not even as a probability, but as a possibility that the evidence does not allow us to rule out. And we can look at what we are currently writing in the rock record, the carbon spike, the warming, the metals, the plastic, the extinction pulse, and ask whether we want this to be the only sentence our chapter contains. Because unlike whatever came before us, if anything did, we have something they may not have had in time: the knowledge that what we do to this planet writes itself into stone. We know we are being recorded. We know the rock remembers. The question is what we choose to say. The Silurian hypothesis is, at its deepest level, a mirror. It holds up the geological past and shows you a reflection that might or might not contain the ghost of another mind. But whatever is in that reflection, whether it shows you an empty canyon or the shadow of something that was once there, it is asking you to look more carefully at the world, at the rock, at the time, at the extraordinary, humbling, vertiginous fact that we are here at all, on this ancient and restless planet, conscious enough to wonder about the ones who might have been here before us. That's where the science ends, and where the wondering begins.